In this video, we will explore acid-base reactions and in particular explore neutralization reactions. And these are another type of reaction that we commonly see happening in aqueous solution. We'll start out with some basics. An acid is a substance that ionizes in aqueous solutions to form H+ ions. In general, acids have a sour taste. They're H+ or proton donors, so you'll see me say, instead of H+, often you'll see me just say proton. Why do you think that is? Because an H+ ion is just a proton. Because protonium, which is the most common isotope of hydrogen, is just one electron, and one proton has 0 neutrons. And so when it loses its electron, it's just a proton. Okay. Acidic solutions also have high concentrations of H+ ions. Now, this definition that I gave you is one of 3 working definitions of acids. This is the Arrhenius definition. There will be more definitions that we will explore in General Chemistry 3. So for some examples of acids, one that most people have heard of is hydrochloric acid, HCl. So as a liquid, HCl can be diluted in water, which is also a liquid, and it will dissociate into H+ ions and Cl- ions. So it has now ionized in an aqueous solution and formed H+ ions. That is the definition of an acid. Let's look at another example. H2SO4, sulfuric acid. In an aqueous solution, this will also ionize to form H+ ion and HSO4-. The great thing, or the interesting thing about sulfuric acid is it's diprotic. So it can undergo another reaction, another dissociation, where it loses its second H+ ion. And now we have SO4 2- as a product. So we call this polyprotic. Bases are substances that produce OH- ions in solution. In general, they have a bitter taste, and basic solutions have a higher concentration of OH- ions over H+ ions. So some examples are common cleaning products and ammonia-based fertilizers. So let's look at some examples. Our first example, we have sodium hydroxide, NaOH. Which usually comes as a solid. We can dissolve that in water and form Na+ ions in aqueous solution and OH- ions in aqueous solution. So we have directly produced OH- ions. Now, we don't have to have something that directly produces those OH- ions. We don't have to ionize directly. We can produce OH- ions in other ways. So for example, we have ammonia. It can react with water, and ammonia is so basic it would prefer to have this proton than water, and so what happens is we end up with an ammonium ion. It's dissolved in water, and we have OH-. So this is an example where the base doesn't directly ionize to produce OH- ions. We also call OH minus ions hydroxide ions. This was in your polyatomic ion table. Just as a reminder, you'll hear me talking about hydroxide ions often. So there are strong acids and strong bases, and there are weak acids and weak bases. The strong acids or bases are ones that completely dissociate in aqueous solution. So for an acid, for example, it releases all of its H+ ions. Weak acids and bases have incomplete dissociation, so they only dissociate incompletely. And we saw something here, back in this last slide, that we didn't talk about. This. So far, all we've seen are single arrows, but now I'm introducing this back and forth arrow. This means incomplete reaction or reversible reaction. So this means the reaction can go both ways. So we would indicate weak acids and bases with these equilibrium arrows. Great. Now, did these definitions sound familiar to you at all? Hopefully they do. So we're talking about complete dissociation and incomplete dissociation. Hopefully that reminds you of electrolytes. A strong acid or base is a strong electrolyte, and a weak acid or base is a weak electrolyte. So here's some lists of strong acids and strong bases. We will come back to these often in class. It will help you to move quicker on quizzes and exams and all of that if you have these memorized. So I highly suggest you memorize them. You will likely become familiarized with them as you're doing practice problems in class and your homework. But it wouldn't hurt to make a couple of flashcards to work on these and just get them memorized. You've probably heard of the pH scale before. In general, we measure acidity and basicity by looking at the concentration of H+ ions. That's just the way that chemistry has decided to measure acidity and basicity. There are other ways to do it, but this is the easiest. So these concentrations are usually very small values. So for example, a neutral solution of water has equal concentration of H+ ions and OH- ions. And that concentration is 1 × 10⁻⁷ molar. It's a little bit obnoxious to say that my tap water is 1 × 10⁻⁷ molar in H+ ions. You probably wouldn't go around communicating with your roommates or your parents in that way. And so we've found a more convenient way to talk about the acidity and basicity of things, and that's the pH scale. So P of anything, when we're talking about chemistry, is equal to the negative log of anything. So that means pH is equal to the negative log of the H+ concentration. So the negative log of 1 × 10⁻⁷ is 7. This is our neutral. So an acid is anything where we have a higher concentration of H+ than OH-, and that pH will be less than 7. If we have our H+ is equal to our OH-, our pH is then 7. If our H+ concentration is less than our OH minus concentration, the pH is then greater than 7. So, just as a reminder, if it's been a while since you've taken algebra, because it's a negative log, as the concentration of H plus ions goes up, the pH goes down. So just a kind of a cool little figure showing some pHs of commonly used things. So battery acid is very acidic, household lye, sodium hydroxide is very basic. We've got a bunch of different things here. So blood is slightly basic, and egg yolks are slightly acidic. So this is just kind of for fun. And now let's talk about neutralization reactions. So we're going to expand on acid-base reactions a significant amount later in the class, but this is going to just give you the really general basics. So to keep in mind, just for this section, an acid plus a base usually means that you're going to make salt and water. There are exceptions. We're not going to get into those this quarter. So if we have an example here, we have HCl reacting with NaOH. We're going to end up making H2O plus NaCl. Here's our water. Here's our salt. So, like we did previously in our precipitation reactions, we can just say, oh, well, our H goes with our OH, and our Cl and our Na go together. So this is another example of what we call a double displacement. Precipitation reactions and neutralization reactions are examples of double displacement reactions. So let's practice writing our molecular equation and our net ionic equation for this reaction. Well, this is the molecular equation that we just wrote. That's great. So let's draw out the complete ionic equation first. So we have H plus Cl minus plus Na plus OH minus goes to H2O. We are not breaking that up. It's a molecular compound held together by covalent bonds. So we don't break that up. But Na plus and Cl minus are independent in solution, solvated by water. So if we want the net ionic equation, we're going to cut out our spectator ions, which are Na plus and Cl minus. Those haven't changed. So now our net ionic equation is H plus aqueous plus OH minus aqueous goes to H2O. So in this question, we're looking at writing out the molecular and net ionic equations for the reaction between HCl and milk of magnesia. Milk of magnesia is a strong base, magnesium hydroxide, that is insoluble in water. So it looks like this white suspension. So we'll start by writing MgOH2 solid plus HCl aqueous goes to, so again we're looking at a double displacement reaction, and we know we're going to make salt plus water. So we'll have our OH form water with our H, and we're going to make MgCl. We should find, there's our water, plus MgCl. But we can look at this and say, well, we know OH, hydroxide, is a -1, Mg is in group 2A, so Mg would be a 2+, therefore this would need to be MgCl2. So let's do that in the same color. We also now need to go back and balance this equation. We have two OHs here, so we have 3 hydrogens and 2 oxygens. So we're going to need to have a 2, at least a 2 in front of our H2O, and we're going to need to have a 2 in front of our HCl so that we have the correct number of chlorines. So let's check in our reactants now. We have magnesium, oxygen, and hydrogen. We'll have 1 magnesium. We will have 2 oxygens. We'll have 4 hydrogens and 2 chlorines. In our products, we have magnesium, oxygen, hydrogen, and chlorine. We have 1 magnesium. We have 2 oxygens there. We have 4 hydrogens there. And we have 2 chlorines. So now we're balanced. To write out our net ionic equation, what we're interested in is the things, the species that change. So we'll need our OH2 and our H. We know that with HCl it's completely ionized in solution because it's a strong acid. So the Cl- isn't going to change because magnesium chloride is also soluble. So let's write out the complete ionic equation to convince us of this before we write out the net ionic equation. So complete ionic equation is MgOH2. This has to stay together because it's a solid, just like we saw in the last video with precipitation reactions. Now we have 2H plus and 2 Cl minus, both in aqueous solution. This is going to go to 2H2O liquid plus Mg2 plus 2 Cl minus, both in aqueous solution because that's soluble. So now we say, well, the only things that really didn't change was our 2 Cl minus, because our Mg2 plus over here is in a solid form here. So our net ionic equation would still have our MgOH2 solid, and we would include our 2H plus, and now we can go to our 2H2O plus Mg2 plus aqueous. 200 mils of a 1 molar solution of HCl with 0.05 molar of NaOH. And I want to know how much NaOH do I add to my acid. So let's write out the reaction first. We have HCl aqueous plus NaOH aqueous. This is going to go to salt and water. Now remember, if we have more of the base, then that means it's a pH greater than 7. And if I have more of the acid, it's a pH of less than 7. And what I want to do is neutralize this. So I want a total pH equal to 7 at the end. That means I have to have the exact same amount in moles of HCl and NaOH. So in order to do this, I'll set up a dimensional analysis. I'm going to start with the amount of my HCl, because I have both amount and concentration here, and I want to find the volume of NaOH. So I've been given 200 mils of HCl. I want to find volume of NaOH. Let's set it up. 0.200 liters of HCl. I want to convert that to moles of HCl. We know that we have So to do this, we'll start with our volume of HCl. And we want to go to moles of HCl, and we can use concentration as our conversion factor. We know that for every 1 liter of HCl, we have 1 mole of HCl. And now we want to get the same number of moles of HCl as NaOH, or same number of moles of NaOH as HCl. And this is a 1-to-1 molar ratio in our reaction. So 1 mole of HCl, need 1 mole of NaOH. And now we convert from moles of NaOH to liters of NaOH using our next conversion factor, which is concentration of NaOH. We know the concentration of NaOH we've been given is 0.05 moles per 1 liter. So now we've started with volume of HCl, we've gone to moles of HCl, we've gone to moles of NaOH, and now we've gone to volume of NaOH. We should get 4.0 liters of NaOH. Often, neutralization reactions in the lab are done via a procedure called a titration, where this can be done where one substance is of known concentration, like we saw in the previous example, and the other substance has an unknown concentration, where in the previous example we had an unknown volume. Now we can have an unknown concentration. So we do this with a device called a burette, and we will titrate in some sort of substance into another substance. So in this example, we have a acid in the flask and a base in the burette. And we titrate in the base to the point where we have neutralization. And in this particular instance, it is determined by a color change. Sometimes we can have a pH meter in there, and sometimes it's just a color change. And at the point of neutralization, we call that the equivalence point. So the point in titration where the amount of titrant, so it should be titrant added is enough to completely analyze or neutralize the analyte solution. So let's look at an example. So if I have a solution of sodium hydroxide, again the base in the burette, with an unknown concentration. So this is NaOH, concentration unknown. I have 200 milliliters of 0.1 molar solution of the strong monoprotic acid potassium hydrogen phthalate. We call that KHP, 0.1 molar, and 200 mils. And as I add the NaOH to the flask, I reach the equivalence point, denoted by the change in color, after I've added 20 mils of sodium hydroxide. So the question is, what is my concentration of sodium hydroxide? So we're going to approach this problem in a very similar way to the last problem. We're going to use dimensional analysis, where our given is the 200 milliliters of 0.1 molar of KHP, and my find is the concentration of NaOH. So we'll start again with the volume, 0.200 liters of our KHP, and we'll convert that to moles of KHP. We know that we have 0.1 moles per 1 liter of KHP, because that was given as our concentration. Now, KHP is a large molecule, so I'm not even going to write this out, but I'm saying here that it's a strong monoprotic acid. That means I only have one H plus that's going to react with each of my OH minuses from sodium hydroxide. So here is my net ionic equation. This is actually what I'm interested in. So I'm not even going to worry about my spectator ions, which are sodium and the potassium hydrogen, or the potassium phthalate. So, if I know that this is the reaction I'm doing, it's a 1-to-1 stoichiometric molar ratio. So if I have moles of KHP, I want to then figure out how many moles of NaOH. So 1 mole of KHP to 1 mole of NaOH. Now what I've been given here, when I run this math, I will end up with moles of NaOH. This is moles of NaOH that I added to get to equivalence point. At that point, my moles of NaOH will equal my moles of KHP. When I know the moles of NaOH, this is our first step, then I can take that and divide it by the volume of NaOH, which, hey, we have that right there, and we can calculate the concentration. So if I do this math, 0.2 times 0.1 divided by 1 times 1 divided by 1, we're looking at 0.02 moles of NaOH. More sig figs. And then our next step is to take that 0.02 moles of NaOH and simply divide that by the volume in liters, 0.020 liters, to get our concentration.